Hello everyone, today we are presenting our solution for Aspen Tech Academic Innovator Challenge, focusing on crucial economy. Our project addresses a critical environmental crisis in Kuwait, the staggering rise in plastic. Currently, plastic make up approximately 15 to 20% of Kuwaiti total waste stream. The majority of the constants of single-use films, practically polyethylene, which is used extensively in our local restaurant and retail sectors. The gap we identify is the conventional mechanical recycling simply isn't effective for this type of films. Instead of allowing this waste to overflow our landfills, we propose a chemical recycling strategy using Aspen HYSYS to transform this plastic to high-value fuel products.
To solve this problem, we developed a thermochemical conversion process, modeled in Aspen HYSYS V10. Our strategy focuses on three specific monomers: styrene, cyclopropane, and ethylene. Using the Peng-Robinson equation of state, we simulated a conversion reactor operating at 450 degrees Celsius. What makes our solution unique is our sensitivity analysis. We didn't just create one model, we developed 4 distinct models to test how different batches of plastic waste affect our fuel yield. One of our most significant findings in HYSYS was that the reactor operates exothermically. This means the process releases energy, allowing for heat integration that reduces the need of external heating, making the entire system more sustainable and cost-effective.
Looking at our result, Model 3, our high cyclopropane feed emerged as a winner, producing a total fuel output of nearly 33 kg per hour. This data provides that by optimizing the feedstock, we are significantly maximize gasoline and diesel production.
Finally, we validated the feasibility of this project by scaling the simulation up by 10 times. The model maintained perfect conversion, providing that is ready for industrial application. Our solution offers a technical roadmap for Kuwait to transition from simple waste disposal to resource recovery. By reducing landfill pressure and providing a local fuel source, we are bringing the circular economy to life. Thank you.
And now I will be diving deeper with you into the simulation that we have created. As you can see here, we have created 4 models, and I am going to start with the first model. We have the mixed plastic feed in the beginning that goes into a conversion reactor, then into a cooler, into a separator, a splitter, and lastly into a second splitter. Now, as for the composition, for the mixed plastic feed, we have chosen styrene, cyclopropane, and ethylene as they represent the monomers of the polyplastics that we want, because the polystyrene, polypropane, and polyethylene do not exist in the component list of Aspen HYSYS. And in this feed, we chose equal amounts of each. Then we put them into a conversion reactor to break the monomers more down. Then we took that vapor, we put it into a cooler to cool it down from 45 Celsius into 440 Celsius. Then we took that liquid product and we put it into a separator to separate the light hydrocarbons and the heavy hydrocarbons, as our targeted products are gasoline and diesel, which are both a heavy hydrocarbons. Then we put it into a first splitter to split both gasoline and diesel from the other heavy hydrocarbons that are in the feed together. Now, as for gasoline, we chose cyclooctane to represent it and hexadecane to represent diesel. So then we took that product, we put it in another splitter, and this splitter splits both of them evenly, as we mentioned. Now, We can see in the product stream the mass fractions of each product. For the gasoline, we have 8.7, then 19.1 for the diesel. Now, why do we have multiple models? Because we wanted to see how different mass fractions of each monomer affects the product. In this second model, we chose a composition that relied heavily on polystyrene, and this made the product more heavy on the hexadecane. As you can see, we have a larger number. Then, in here, this feed relied heavily on cyclopropane, which made the feed more composed of hexadecane. As you can see, it is almost double of the amount in the beginning. Lastly, in the fourth model, here we chose a composition that relied heavily on ethylene, which gave us a product that is more hexadecane heavy. And as you have noticed, both model 3 and 4 almost have the same amount of both gasoline and diesel. That is because both ethylene and cyclopropane have similar chemical structure and are heavy, so they produce the heavier.
To the end, our simulation confirms that a cleaner, more efficient future for Kuwait is technically feasible. Now, it's time to turn these digital insights into industrial impact. Thank you so much for watching, and thank you for your attention.